Hello, welcome back. This is the second video of a playlist about the preparation of phenols. There's a PDF version of this presentation under the Community tab of my channel. This video is about the preparation of phenols by aromatic nucleophilic substitution, for instance of halides by hydroxide or alkoxides. Treatment of chlorobenzene with sodium hydroxide was one of the first processes for the industrial production of phenol, but has been replaced by the Hock process discussed in part 1 of this playlist. Aromatic nucleophilic substitutions can proceed by different mechanisms. If a given aryl halide has electron withdrawing groups in positions 2 or 4, substitution can occur by an addition-elimination mechanism with an anionic intermediate. Fluoride is the best leaving group in such instances, and iodide the worst. Aryl halides without electron withdrawing groups react with hydroxide or other strong bases via an aryne, sometimes formed from a non-stabilized deprotonated arene. Addition of water to arynes then yields 1 or 2 regioisomeric phenols. Aryl iodides react fastest, while fluorides are the most unreactive. Aromatic substitutions of halides can also be catalyzed by transition metals, usually copper. Also in this case, iodide is the best leaving group, while fluoride is the worst. Diazonium salts are readily available from anilines, but are stable only under acidic conditions. Under alkaline conditions, aqueous hydroxide will add to the diazonium group at nitrogen and regenerate a nitrosoaniline. Heating with strong acids, however, can yield a phenyl cation and then a phenol. Phenyl cations can also be formed by protonation of arynes or by photolysis of aryl halides. Occasionally, the thermal decomposition of diazonium salts can also yield arynes. This experiment sheds some light on the mechanism of the nucleophilic hydrolysis of unactivated aryl halides. Strong heating of 4 halotoluenes with an excess of sodium hydroxide yielded an almost equimolar mixture of 2 isomeric cresols, what indicates an intermediate aryne. Iodide was displaced fastest, while fluoride underwent only slow ipso substitution. To prevent any metal catalysis, these reactions were conducted in a glass autoclave. When trace amounts of copper sulfate were added, substitution proceeded faster and ipso substitution became the main reaction path. The relative substitution rates of the 4 halogens remained the same, though. Let's check some specific preparations. First uncatalyzed substitutions and then catalyzed ones. Heating chlorobenzene with 2 equivalents of aqueous sodium hydroxide to 400 degrees Celsius for 12 minutes gave mostly phenol, along with diphenyl ether and 2-phenylphenol. These are typical byproducts that can only be avoided by diluting the reaction. Selective substitutions at polyhalobenzenes can make sense if the purification of the target product is easy. 2,5-dichlorophenol, for instance, the main product of this reaction, is an intermediate for the manufacture of dicamba, an important herbicide. The conditions shown here only yielded about 40% of this phenol, but its separation from the other 2 isomers was relatively straightforward. Because the starting materials are inexpensive, this is indeed a viable preparation of 2,5-dichlorophenol. Aryl halides activated by electron withdrawing groups react much faster with hydroxide than unactivated halides. 4-chloronitrobenzene, for instance, can already be hydrolyzed at 170 degrees Celsius. No isomers were formed, what indicates that the substitution proceeded by an addition-elimination mechanism. With stronger nucleophiles, such substitutions can occur under still milder conditions. Here a mixture of terz-butyl hydroperoxide and potassium terz-butoxide in liquid ammonia was used. Interestingly, with an excess of butoxide, the main reaction became an oxidative hydroxylation to yield 4-chloro-2-hydroxynitrobenzene. I've sketched here a possible mechanism to account for this unexpected result. Addition of nucleophiles to unsubstituted positions of nitrobenzenes is faster than addition to substituted positions. These additions are reversible though. With a large excess of base, the 2-peroxy intermediate eliminated an alkoxide and yielded the observed 2-hydroxynitrobenzene. With only a slight excess of base, however, the intermediate formed by addition of the peroxide to the chlorine-substituted carbon would have time enough to irreversibly eliminate chloride or chlorinate some nucleophile present in the mixture, for instance ammonia. Unactivated aryl bromides are a bit more reactive than aryl chlorides. Here, bromobenzene was converted into a terz-butyl ether with potassium terzbutoxide in DMSO. Dipolar aprotic solvents increase the nucleophilicity of anionic nucleophiles, but unfortunately DMSO and DMF are unstable toward strong bases and may undergo violent decomposition under the conditions shown here. Dimethylacetamide or sulfolane might have been a safer choice in this case. Another safer alternative to DMSO or DMF are crown ethers or polyethylene glycol. Here an aryl bromide underwent nucleophilic substitution with potassium terzbutoxide and stoichiometric quantities of 18 crown 6 in THF. An arine was formed as intermediate and no displacement of fluoride occurred. Fluoride is only easy to substitute in arenes activated by electron withdrawing groups, as in this example. Neither heating nor crown ethers were required, and the target terzbutyl ether was formed in high yield. No reaction occurred, however, with an isomeric starting material with a methyl group para to the nitro group. Such nitrotoluenes are acidic, and deprotonation slows down nucleophilic attack by the anionic terzbutoxide. Sometimes it's possible to displace halides sequentially, even fluoride. Here 1,3-difluorobenzene was treated first with an excess of benzyl alcohol and potassium terzbutoxide, and a clean substitution of only one of the two fluorine atoms occurred. The second fluoride was displaced with butanol under conditions like those of the first substitution. In this example, one fluoride of a trifluoroaniline was displaced selectively by hydroxide. Oxone enhanced the nucleophilicity of the trifluoroacetyl group and thus promoted the intramolecular aromatic substitution of fluoride. An older strategy to prepare phenols is by heating arene sulfonates with sodium hydroxide. Again, like in the displacement of unactivated chloride, a high reaction temperature is usually required, as in this example. Resorcinol has also been prepared this way. The starting material was readily obtained by twofold sulfonylation of benzene with sulfuric acid containing sulfur trioxide. Occasionally, even anilines react with aqueous acids or bases to phenols. Here, an excess of hot aqueous sodium hydroxide transformed 4-nitroaniline into 4-nitrophenol quantitatively. Anilines devoid of activating groups can also be hydrolyzed to phenols. In this example, aniline was heated with aqueous phosphoric acid to 290 degrees Celsius for 1 day. A mixture of phenol and diphenylamine resulted. Elemental nitrogen is about the best leaving group known, but diazonium salts are also powerful oxidants and tend to react with nucleophiles not at carbon but at the terminal nitrogen atom. The conversion of aromatic diazonium salts into phenols thus requires heating with strong, non-reducing acids. One further problem of these reactions is occasional strong foaming. Here, 3-nitrophenyl diazonium bisulfate was added in small portions to hot sulfuric acid to prevent excessive foaming. The expected phenol was obtained in excellent yield. This example is similar to the previous one and shows that under these conditions no arines are formed. A clean ipso substitution of nitrogen occurred. Because diazonium groups are strongly electron withdrawing, 2 or 4 halobenzene diazonium salts readily hydrolyze to 2 or 4 hydroxybenzene diazonium salts, but this did not occur here. In this example, methylantranilate was diazotized and then treated with an aniline under slightly alkaline conditions. The aniline added to the terminal nitrogen atom and a triacinone was formed. Heating with trifluoroacetic acid regenerated the diazonium salt and led then to the expected phenol. Also, aromatic nitro groups can be displaced by nucleophiles. Direct substitution with hydroxide does not work well, but with a deprotonated benzaldehyde oxime S nucleophile, phenols can sometimes be obtained in high yield. strong bases cleave the intermediate O-aryl oxime into benzonitrile and the target phenol. The conditions shown here are only applicable to nitroarenes with additional electron-withdrawing groups. With 4-fluoronitrobenzene, exclusive displacement of fluoride occurred, and a mixture of 4-nitrophenol and the intermediate arylated oxime resulted. Instead of sodium hydride, potassium hydroxide can also be used as base. Again, as mentioned earlier, heating mixtures of DMSO and strong bases is dangerous and cannot usually be scaled up safely. Dimethylacetamide, sulfolane or propionitrile would be better alternatives worth testing. If a given leaving group can also stabilize a carbanion, as for instance nitro or sulfonium groups, the nucleophile may attack a position adjacent to the leaving group. Here, a thiophenylsulfonium salt reacted with sodium ethoxide and yielded an unexpected C&EN substitution product. With diazonium salts, such C&EN substitutions are not usually observed because nucleophiles attack diazonium salts at nitrogen. Nitroarenes can undergo C&EN substitution with carbon nucleophiles, for instance with a cyanide in the von Richter reaction. Let's check some practical examples of catalyzed aromatic substitutions. With transition metals like copper, nickel or palladium, these reactions start with an insertion of the metal into the carbon-halogen bond, followed by exchange of the halide by hydroxide and reductive elimination of the metal. In this example, 2-chlorophenol was heated with a slight excess of hydroxide and a small amount of copper powder in water. The substitution proceeded faster than without copper and no arynes were formed. In addition to catechol, a bit of phenol and dihydroxydiphenyl ether were also obtained. The catalytic efficiency of copper can be enhanced with ligands, which maintain the metal in solution and can control electron density and steric accessibility of the metal. Here, an oxalic acid anilide was used in combination with copper acetylacetonate to catalyze the alkaline hydrolysis of 4-tertsbutoxychlorobenzene. The expected phenol was obtained in 80% yield. Hydroxyquinoline N oxide is another suitable ligand for such reactions. Here 2-chlorobenzaldehyde was converted into salicylaldehyde in 75% yield, without much Cannizzaro reaction. In this example, a selective monosubstitution at a dichlorobenzamide succeeded with 10% of a copper phenanthroline catalyst. The insertion of palladium into carbon-chlorine bonds usually requires electron-rich, bulky phosphine ligands like the one in this example. The conditions were only slightly alkaline and milder than those of copper-catalyzed substitutions. This example is similar to the previous one. Hydrolysis of the unactivated aryl chloride was complete after only half an hour at 115 degrees Celsius. Similarly, here the aromatic substitution was conducted in dioxane at only 80 degrees Celsius. Aryl bromides react with transition metal catalysts about 10 times faster than aryl chlorides. In this example, 1,3-bromochlorobenzene was transformed into 3-chlorophenol with 5% of a copper oxalamide complex, in excess of benzaldehyde oxime and cesium carbonate. No substitution of chloride occurred. Here, 2-bromoanisole was converted into guaiacol with an excess of potassium hydroxide and only 2% of a copper complex in sulfolane. Even glycolic acid can promote copper-catalyzed substitutions of unactivated aryl bromides, as shown here. Aryl ether formation was prevented by the large excess of sodium hydroxide. In this example, a protected 3-bromoaniline was converted into a phenol with 5% of a nickel catalyst. Unlike in the copper-catalyzed reactions, no strong bases were required. The silane generated nickel-1, the active catalyst. Aryl iodides are highly reactive but more expensive than bromides or chlorides. Here, a substituted methyl 4-iodobenzoate was converted into a phenol with an excess of potassium hydroxide and 10% of a copper hydroxyquinoline complex. Aryl fluorides devoid of electron-withdrawing groups do not readily undergo aromatic nucleophilic substitution. Here, with the aid of 10% of silver triflate and catalytic rhodium, the authors substituted fluoride selectively in the presence of bromide, but such examples are rare and of limited practical relevance. One industrial strategy to manufacture phenol is by copper-mediated hydroxylation and decarboxylation of benzoic acid. Stoichiometric quantities of copper too were used in this example. The required high temperatures make this method unsuitable for laboratory preparations of structurally more complex phenols. This here is a newer variation of this strategy. The reaction was conducted at 400 degrees Celsius in the gas phase and yielded directly a mixture of phenol and benzene. I've sketched here a different mechanism than on the previous slide, and both seem realistic to me. What we know for sure is that no ipso substitution of the carboxyl group, but an orthohydroxylation and decarboxylation occur. So, what can go wrong? I already showed you one example of oxidative hydroxylation of a nitroarene. These reactions are discussed more thoroughly in part 3 of this playlist. In this example, such a hydroxylation occurred without any added oxidant. Nitroarenes can, of course, also act as oxidants and may even decompose violently when heated with alkali hydroxides. Here, only 13% of a phenol resulted after refluxing for 3 days in benzene. In this example, both oxidative hydroxylation and substitution of a nitro group occurred. With stoichiometric oxidants, much higher yields can be attained, as in this example. If too little hydroxide or water is added, diaryl ethers can be formed. This can be a problem with very lipophilic starting materials. In such instances, phase transfer catalysts or terz butoxides may be used to suppress diaryl ether formation. Here are some further examples which you can also find in the description of this video. The next video of this playlist is about the preparation of phenols by electrophilic substitution, for instance by direct oxidative hydroxylation, as we just saw. So long